start the session. So it's my great pleasure to introduce our invited speaker, Dr. Kenneth Stanley, who is a professor of the Electrical Engineering and Computer Science Department at UCF, University of Central Florida, where he also heads HIPLEX, Evolutionary Complexity Research Group. Dr. Stanley got his PhD in 2004 at the University of Texas at Austin. Ken Stanley developed a method called NEAT, Neural Evolution of Augmenting Topologies, which, starting with a simple network, progressively increments the complexity of the network by adding new neurons and new connections. He also has contributions to topics like machine learning for video games and interactive evolution, among many others. However, today's talk, I believe, conveys the main idea of avoiding searching for objectives, but instead advocates search for novelty or novel behaviors. Therefore, don't expect me to tell you what's the objective of this talk. I will not be able to do that, but I expect that you can open your minds to what promises to be an exciting and innovative, although maybe polemic message, which I anticipate as very challenging. Professor Kenneth Stanley, thank you so much for being with us. Thank you.
Okay, thank you. I just, like other keynotes, I wanted to just say that it's a real honor to be here. Very happy to be able to be here in this beautiful island, and thanks to the committee for giving me this opportunity. I'm also very honored that you actually got up after last night's dinner, and you're actually here now, so it's double honor. What I wanted to start with was pointing out that algorithms are not only in computers. And if you think about life and society and how it works, we see algorithmic processes in many facets of life. So everything from education to research and funding and how we decide what to fund, which is supposed to facilitate creativity and innovation, entrepreneurship and investing. Even the pursuit of happiness, in some sense, does involve some algorithmic process. Is this okay? So, what I want to ask then, given that we see algorithmic processes in life, and of course life is a lot about intelligence, and intelligence is behind a lot of these aspects of what we do as people and as a society, wouldn't you expect that sometimes insights in artificial intelligence would inform back to human endeavors? And what I want to do today is I want to give you a little story about an idea in AI that has a lot of implications way beyond AI itself. So I think you find that pretty interesting. And to do that, I'm going to start in a bit of a strange place with a website called PickBreeder. Now, if you bear with me, I want to explain why I'm starting here. This is a picture breeding website. So human beings are coming in on the internet and actually breeding pictures in a crowdsourced setting. It's basically an online service that you could even use right now. And the reason that I'm going to talk about PickBreeder first is because what we're going to see is that people on this site are making discoveries. And the way that they make discoveries turns out to reveal something about the nature of discovery itself, something deep and fundamental that I think you'll find really interesting. And so I want to give you the full picture of how this is happening, because then we're going to take that insight and expand it and think about what it means for algorithms and eventually for life itself. So this website has been around for 6 years. There's a lot of images have been involved. more than 9,000 images, and we have had over 900 users registered, plus some anonymous users too. If you've seen biomorphs, if you've heard of that, and if you've read The Blind Watchmaker, which is from Dawkins, you'll recognize some things about this. It's kind of like biomorphs on steroids. If you don't know what that is, it doesn't matter. I'm going to show you everything you need to know. You'll understand it. And what is really going to be important from this first part of this talk is to see how it is that the users of this website began making really surprising discoveries, as you'll see. So what I want to show you first is just what happens if you go to PicBreeder and just start going from scratch. And what I'm going to do is build up and kind of show you how it works, and then you'll get to see these discoveries that are being made. It's deceptively simple. So if you go in, and this is sometimes called evolutionary art, if you go to PicBreeder and you start breeding from scratch, what you will be presented with is basically a set of blobs, random blobs like these, and from these you would pick the one that you like maybe the best. So like say if I like that one, I think that's interesting. Then what I'm doing is basically like animal breeding or you know, dog breeding or horse breeding. I'm choosing parents that I like and then creating children or offspring from them. So if I choose this and then say I want to evolve from here or breed this, then it becomes the parent and the next generation of children, you can see the family resemblance. And so then I would continue with this process iteratively. So I could say, oh, well, this one looks maybe more interesting than the other ones. So I'll choose that, and that one leads to then these children, and so on. And if I find something, and this is the kind of interesting thing about this website, if I find something that I think is interesting or worth sharing, I can click on it and then ask to publish it to the world. So that you can see that actually there's a publish button here. And so then it becomes part of the website permanently that everybody in the world now can see that I've discovered. So this is really the basic idea. Now, what I also want to show you, and if you'll just give me a brief moment to go in a digression and tell you a little bit about the underlying representation, because it will help you to appreciate how extraordinary the discoveries that we're about to see are. So I want you to understand what it is that people really are exploring when they're choosing pictures in this website. Because underneath these pictures, there's a kind of a DNA, or you could think of it as the genetics behind the pictures, which is represented by what are called a compositional pattern producing network. That's this term here. But don't let that term distract you. It doesn't matter what we call it. All it is that inside of each one of those pictures is a network that looks like this, which is a set of simple functions that are composed with each other, so that's where the word compositional comes from, to output a picture. And basically, this composition here is used to compute a function of x and y. So basically, we have x and y inputs coming into this network. It's sort of like a neural network. And coming out is hue, saturation, and brightness, or color. And so if we query every xy point in this plane and say, ask this network for an output, and say, what is the color? Then if we paint those colors, basically we are graphing the pattern encoded by this composition. And by composition, what I mean is that if the output of this Gaussian function is fed into the input of this sigmoid, which is what this connection means, that's basically called function composition. What we're doing is composing the Gaussian with the sigmoid. So we're using function composition here. These weights also, these connections can be weighted. So we have connection weights just like a neural network. So basically the output of the Gaussian will be multiplied by the weight of that connection. And together all of this then defines the function. And really all that's happening here is we're graphing the function that's encoded by this composition. That's what's happening. And the composition is allowed to be made of only 4 key canonical functions. There's a Gaussian, a sigmoid, a sine, and linear. And those are the only things that can appear in here. Now, it's important to note, so you can understand, when you think about, we started with these very simple blobs, how is this going to lead to anything interesting? Well, it's important to note that over the process of this breeding, of this evolution, there is an algorithm underneath called NEAT, which is actually from my own dissertation work. And what NEAT does sometimes is it will add randomly a new node or a new connection to this network, so it's causing the network to expand as evolution progresses. So the network is getting bigger, and that means that the images are getting more complex and can become increasingly complex, so that's why we can get more interesting images. So now just think about this for a second. If you just think about this kind of network, sines, Gaussians, etc., being composed with each other, what do you think the search space is like that's induced by these kinds of compositions? I mean, do you think that it's full of really meaningful images? And I'll show you what it's like. It's not very pretty. It's a desolate space. If you generate random compositional pattern producing networks and just say, well, what kind of patterns do they output? They look like this. These are varying complexity networks. And this is the best that you get. And if you just keep doing this over and over and over again, generating random networks, you basically go forever. You'll never find anything any much better than this. And so this is a very desolate space in some sense. And most of the space in aggregate is basically garbage. So given this, now that we understand what happens on this site, what do you think people would be able to discover in a world that looks like this? And I think it's very surprising, because what people find is stuff like this. It's quite amazing. I think, at least, it's amazing that the users are able to breed this kind of stuff. These are actual discoveries. These are not created by artists. These are actual compositional pattern-producing networks, and there's no retouching here. So these are true discoveries. And if you think about it, it's just remarkable, the natural kind of images that we're seeing, things like a skull, a butterfly, there's a car, there's Jupiter, because there's the red spot, as it should be there. And so it's really surprising that people are making these kinds of discoveries. And you know, if you think about it, it's like these are really just basic functions being composed with each other. It's like if you were in high school math class and your teacher said, give me the equation for a skull. And this is the kind of stuff that people are actually discovering. Now I want to talk a little bit about what's going on and why this is happening and how come people so consistently discover such interesting images. And one important factor that I have not yet mentioned is called branching. Because what you can do on PicBreeder is, like I said, people publish their images so that everybody in the world can see what they've done. And if you come into PicBreeder, you're allowed to browse through the thousands of images that have preceded you by other users, and you can then do what's called branch from an existing image. And that means you can start evolving from an image that someone else discovered. So people are building on each other's work, and in some sense, this branching process, branching upon branching upon branching, is allowing people to create increasingly sophisticated discoveries from each other's discoveries. So just to show you, this is like what the website actually looks like. Like if you visited there, you'd see some options. And if I scroll down, like I'd see these are different categories that you can go deeper into, which have collections of images. And these are what things you could branch from. So, like for example, if I took one of the faces, there's a lot of faces on there right now, but if I found a face and I wanted to, and I said, okay, let's branch from this face, it would look like this from the beginning because I'm starting from a face. So I get face variants. And so then I could just play this game, but now I'm playing the game starting from where that person began. And so I would say, okay, well, you know, maybe I like this face. I like it has an open mouth, I guess. So then that becomes the parent, and so forth and so on. And like before, I can now publish my discovery. So what's happening is that people are building on each other's discoveries by branching. And so what we're getting is basically this growing phylogenies, like in biology. Basically have sort of like a tree of life, but here's just a tree of pictures. And this is just a small subsection of the PicBreeder phylogeny. Of course, there's thousands of images, but it gives you a sense of what's happening. So every connection in this graph is a single user session. The lengths of the connections don't mean anything. So any connection here is a single user session. There could be many generations or many selection steps done along one of these lines. But what's important is that each one of these is a branch where somebody started from someone else's discovery and continued from there. So this growing proliferation of branches upon branches upon branches is why you're getting this kind of diversity happening where people are building on each other's discoveries. But still, now I don't want you to think that that just explains everything, because remember, this is in a space like this. So there's still something really interesting going on. People are building on each other's stuff, but these are true needles in a haystack. When you think about the fact that they come from a world like this, it's still amazing that people are collaboratively, in this sense, coming up with this stuff. So I want to go a little deeper into that. You know, because what we're seeing are entire families of things. I mean, these are actually real close genetic relatives. This is a real family. This is a face family. Everybody's genetically close to each other. Really amazing diversity of images. You know, I mean, just look at this for a second and think about the luck or apparent luck involved in something like the handle on this picture. I mean, what luck did we have that somebody this handle just appeared here appropriately for a picture? Or the stem on this apple. Look at this, it's asymmetric while the apple is symmetric. What kind of luck are we having? Look at the colors on the tropical bird or the planet or the humanoid forms. And it's just remarkable that these kinds of discoveries are being made. Now, I know that, so for some of you, so I'm really trying to convince you that we should be impressed by our users' discoveries. And some of you maybe are impressed, and some of you maybe are less impressed, because there's one kind of question that may be dangling here, which is, wait a second, if I go to PickBreeder and I choose things that look like what I want, like say I wanted to find an apple, well then I would just sort of choose the thing that looks most like an apple, and then in the next generation, I choose the thing that looks most like an apple. And if I keep on doing that, wouldn't I just eventually find the apple? So why should I be so impressed? If the world worked that way, then yes, I would agree with you. That's not that impressive. But what is really fascinating is that that is not how this world works. In fact, you will fail if you come in like that. You will never find something by looking for it. And I want to give you a little more insight into that. I want to give you an insight into how these kinds of images are really discovered, because the way they're discovered is really fascinating. It's not by trying to look for them. In fact, it's the exact opposite. And the reason I can tell you, I can give you a little anecdotal story about this, is because I discovered the car. So you see the car image. So I want to give you the full story behind how I discovered the car, because it's really strange what happened. You see, because if you were searching in a space like this, would you expect to find a car in this space? Now, I never would have in a million years thought of finding a car. In fact, I was not even thinking about or interested in finding a car, because it wouldn't have occurred to me that it's even possible. But I did find a car. And this is why I learned something, because I realized how these kinds of discoveries are made. So the first thing, the most important thing, this is an important ingredient to finding something interesting, is I was not looking for the car. I never thought about even the possibility that I might find a car. Instead, I chose this image, which is an alien. I thought it looks like E.T. It's basically an alien face. Because I thought this is something someone else evolved. I decided to branch from it. And I thought that this might lead to more aliens, and I thought that would be cool. So I thought I wanted to get some more alien faces. But then something started to happen. What happened was the eyes, you see the eyes of the alien, they started to descend relative to the body, and I realized in the middle of this session that I was getting a car. It just sort of started to happen. And in retrospect, you can see why. I mean, look at the wheels and look at the eyes. Clearly related, but only in retrospect. No one in a million years could predict that this face was going to turn into a car, and I certainly didn't. But that's what happened. It was a coincidence, and once I started to realize, then I could follow the path down to the car. So this is a very strange. You think about this, because what it means is that this is true. The only way to find the car was by not looking for it, because if I had been looking for a car, I would never have selected the alien face, because it doesn't look like a car to me. So I had to not be looking for a car to find a car. But it's even stranger than that, because I wouldn't have evolved that alien either. That was someone else's discovery. I would never have done that. So someone else had to do something that I never would have done. And if you put all this together, I mean, just take this story and think about how crazy it is. First, someone had to do something that I never would have done myself, and then I had to not be trying to do what I ultimately did, and only if those two things were true would I ever be able to discover this car. So now you would think, well, that's really amazing. This is a coincidence, basically. A 1 in a million chance that you would ever have a situation like this where those kinds of things are true. But here's the funny thing. That is not a coincidence. This is the story behind every interesting discovery on the site. It's always this story. You never find something by looking for it. You only find things by not looking for it. Look at the top. These are some of the top images, or at least for me, some of the interesting images. And it's the same story. These are stepping stones that led to these discoveries. Like, look at this. I think this looks like an egg with a hat. This egg with a hat led to the pitcher. But I guarantee you that the person who branched from that egg with a hat, and someone did choose that and branch from it, was not thinking about pitchers. It's impossible. Even though, in retrospect, you can see that the lid of this pitcher has some relation, mathematically, to the hat, right? But you still wouldn't think that this is going to become a pitcher. Or here's something, this dish was branched by a user and eventually led to this skull. Could you imagine someone actually thinking that this is just what I need to get a skull? We start with a dish. But this is what happened. Or even crazier is the letter G. It led to Jupiter. It's not even the right letter. But yeah, so you would never think this is you're going to Jupiter. But somebody branched from that and got to Jupiter. And so the story is just over and over again, the same story as what happened with the car. You have to not be looking for it. Someone else has to make a discovery for you to ultimately discover what you discover. You can only find things by not looking for them, because the reason is, and this is a principle for all of search, the stepping stones, the places you have to cross to get to where you want to go, almost never resemble the final product in any complex search space. And this is why true discovery requires this very strange kind of serendipity. Now I want to give you more evidence, because I'm giving you a strange paradoxical story which is counterintuitive. So I want to really drive this home, why this is true. And so this is something that we did which is rather strange. What we decided to do was try to re-evolve the images that had already been evolved. So normally this would not be the most interesting thing to be doing. But it's interesting now because I'm telling you, you can't discover this stuff by looking for it. And so we know that these have been discovered, right? Because people actually discovered the skull and the butterfly. That's one of the early butterflies that was discovered. In fact, if you look at this, the numbers there, these were discovered in under 100 selection steps, which is remarkable. You think about how few generations it took to find something like this. So in some sense, it means these actually weren't that hard to find. Cumulatively, there were 74 selection steps to get to the skull. There was several users branching off of each other, but in aggregate, it was 74 selection steps. So you might think, well, we know we can find them, so this is already known. It's established fact. So let's try to find them again, because we know they exist in the search space. And so let's create an objective function or a fitness function, like a traditional evolutionary algorithm, based on closeness to the evolved image as a target. And we'll use neat again, because neat, remember, is inside PickBreeder. So we'll use the same algorithm now, but we'll put it inside of an automated framework, which is probably more traditional anyway. Just an automated search algorithm running in the background, looking for the skull and the butterfly based on image matching. And so that should align with your intuitions about this idea that, oh, I could just look for the apple and I would eventually find it. So basically, we'll look for the skull and hopefully we'll find it. And what happens is, it's really interesting, is that it's just terrible. I mean, these are the best results. Each one of these was a 30,000 generation run. Remember, these were found in under 100 generations originally. We gave it 30,000 generations. Same underlying algorithm. Only difference here is that the objective is to match the target. And this is the best we got in every single run. Just miserable results. Now, if you saw this, like if this was like a benchmark that I was publishing at a conference, and I was like, you know, everybody in the world wants to get skulls or something, and I published this paper that said, we tried to evolve the great skull with neat, and this is what we got, you would just say, well, there's something wrong here, something wrong with neat, right? I mean, the algorithm is failing to achieve the objective. But you can't say that in this case, because this is a special case, because these were discovered with neat. So you can't argue that they can't be discovered with neat. Something else is wrong here. There's something wrong with the objective. You see, the problem is, being close to the target is the wrong metric for progress. You might be thinking, well, you know, he didn't really describe the fitness function exactly. Maybe he needs a better image matcher. You know, maybe we could use some vision algorithm to match better. But that's wrong, because a better image matcher would be worse. Because look, the stepping stones, and I'm showing you here some of the stepping stones that lead to the skull, they don't look like a skull. So what good would it be if you had a really good skull matching algorithm? That would not cause you to reward this donut. You've got to go through the donut to get to the skull. The donut doesn't look like a skull, so it doesn't matter how good your image matcher is. The point is that what we're seeing in the search space is what's called deception. It's that the stepping stones don't resemble the final target, and so it doesn't matter how good you are at describing your final target, it won't help you get there. And so this is just the wrong way to make these kinds of discoveries. Humans chose these stepping stones. Every one of these was chosen by a human being because they were interesting for other reasons, not because that anyone thought that these were leading to a skull. Nobody thinks that donuts lead to skulls, even though this donut does lead to a skull. Humans chose these for other reasons, and that's why we get all of these stepping stones. In some sense, what's happening inside a pick breeder is that pick breeder is a stepping stone collector. It collects things that lead to things, and it's growing in its collection. And those things, because it's a stepping stone collector, open up more and more possibilities. But none of the discoveries are happening because someone's trying to go somewhere in particular. People are going everywhere and nowhere, and it's collecting all of these stepping stones, and that's why we're getting to so many interesting places. But you can't get there by trying. And this is a good challenge, too. I challenge anybody to try to get the skull with a CPPN. I would suggest to you it will never happen again. It's a one-time occurrence. And this is a universal story. The stepping stones almost never resemble the final product. And we've seen now a lot of examples of this. And this is why you can't find things by looking for them. Okay, so think about the implications of this now more broadly. This is an observation that we made inside of PickBreeder, this online service that we put up several years ago. But it leads to these really strange statements. Like, I mean, there's a lot of ways I could say basically the same thing. Like, for example, the path to success is through not trying to succeed. Or, to achieve our highest goals, we must be willing to abandon them, right? Because the only way to get to this goal is by not trying to get to this goal. So you have to abandon it in order to have it be possible to happen. It is in your interest, and this is true, it is in your interest that others do not follow the path that you think is right. Because if you think about it, those are the people who will lay the stepping stones that will lead to your greatest discoveries. The only reason this is working is because people are doing things that their peers would not do. Just like the person who found the alien face did something that I would never have done before finding the car. And so we need people, for discovery to work, in aggregate, as a society, to be doing things that we don't believe in. Because they're creating the stepping stones that lead to our greatest discoveries. Now, think about this. Hold on a second. These implications are not about computer science. If you read this slide, it doesn't really necessarily, you could be talking about sociology here. And that's really interesting that this is coming from observations from, originally, experiments in artificial intelligence. So hold that thought for a second. I want you to remember that because I'm going to come back to this idea that we have implications here that are much broader than just artificial intelligence. But first, before I give you some of those, I want to talk about extending this a little bit algorithmically to show you where we can go with this. So what if, now think about this, like if you think about PickBreeder, what does this mean in terms of automated search algorithms? I mean, how many algorithms in artificial intelligence and machine learning have an objective function, are driven by an objective? And what does it mean that we've seen the principle now that you can't find anything interesting if you have an objective? And so maybe, would it be interesting, or how would search work if it didn't have an objective, an explicit objective? What if we tried, in an automated sense, instead of trying to go towards a specific target in the search space, we tried to make a stepping stone collector that works in a similar way to PickBreeder instead of worrying where the search is going. And so this is the algorithm we came up with. We thought, okay, let's try to do this. Let's abandon objectives and search instead for novelty. And this is called novelty search. It was introduced a few years ago. Now here's the logic. Let me give you a logic a little bit. What we're saying is it's hard to identify stepping stones a priori. It's hard to know what the steps are that might lead to the objective. Almost always there's going to be deception. If there wasn't deception, the problem would be trivial, right? I mean, the reason that problems are hard is because of deception. And that's why we're using search algorithms. We don't need to use search algorithms if we already know all of the stepping stones that lead to the objective. So we don't know the stepping stones. And so what if then we look for some proxy for stepping stones? Now I would suggest that in PickBreeder the proxy is interestingness. You know, people are choosing things because they're interesting for many diverse reasons. You know, like that donut. I don't know why the person chose the donut, but it was interesting to somebody. They saw a donut and liked it. Now, it's very hard to formalize interestingness, and I would say it's almost an AI complete problem. But novelty is a pretty good approximation of interestingness. I mean, if something is truly novel, really different from anything you've seen before, there's a good chance that this is something interesting. And something that's different can lead to more things that are different. So it's a potential stepping stone. So let's collect novelty. Let's collect novel things in the search space. Now, sometimes people would react to this suggestion and be a little worried because you think, well, this is kind of like, there's no information in a novelty search. You know, it doesn't know where it's trying to go. So what assurance do we have that it will find anything interesting? But the thing is, actually, there is a lot of information in novelty search. It's still information rich. I mean, if you think about objective-based search, searching for an objective, the information you have is the objective. But what you do in an objective-based search is you compare where you are to where you want to be. That's the driving force in objective-based search. Well, novelty search is just the opposite. You compare where you are to where you have been in the past. So there's just still information. It's just information from the past. But in fact, this is better information in some sense because we know about the past. We have complete information about the past. We know everywhere we've been, so we can approximate novelty with high accuracy, whereas the objective is in a haze, a cloud of fog. We don't know much about the future. We know about the past. So in some sense, there's more information and more accurate information in novelty search. And so there is no final objective in this kind of search, and since we're not trying to go anywhere in particular, just find new behaviors. But here's something weird about this kind of search. We will find that we can discover solutions to problems without looking for them. Sometimes better than if we are looking for them. And if that sounds strange, well, it should make some sense, at least in the context of what I just showed you with PickBreeder. Of course, sometimes it is better not to be looking for the objective in order to get somewhere interesting. So I want to test this in front of you. I want to show you a couple results from novelty search. And so what I'm going to do is start again with NEAT. We'll use the same evolutionary algorithm, but this time, instead of evolve pictures and pattern-producing networks, we'll evolve artificial neural networks, basically little brains, to control simulated robots. And so we'll be looking for novel behaviors. And we're not going to have the traditional fitness function, which is what you'd have in an evolutionary algorithm or an objective function. Instead, we will just reward any behavior that's novel so far. So we don't have a concept of better or worse. We're agnostic about what's good or not good in the search space. There's no global sense of better or worse. Everything is completely relative to where you've been before. There's no final objective in the sense there's no target that you're aiming at. And it changes over evolution, of course. What's novel in the past is no longer novel in the future. And that's what we're going to do. Now, there's one other objection I want to address, which is, of course, this makes people uneasy because it's a very strange kind of a search. And one of the reasons is because you think, is this kind of like exhaustive search? I mean, if you just enumerate all the possibilities in the search space, that's not the most interesting algorithm. I mean, yes, eventually you'll find everything, but nobody would want to actually do that. But this is not like exhaustive search. And I want you to have an intuition about that. Because novelty search induces an order in the search. Remember, NEAT can increase complexity. And in fact, what a novelty search is doing, if you think about what it means to continually discover novelty, it is inducing an order from simple to complex. Basically, it's climbing the ladder of complexity. Because once all the simple behaviors that exist are exhausted, there's only one way to become more novel, and that is to become more complex. Because there's nothing left in the simple space. And so complexity will inevitably increase. And another way to say that is that novelty requires accumulating information. Complexity and information go hand in hand. Like, think about walking on the moon. That was an amazing accomplishment for humankind, and it was very novel. No one had ever walked on the moon before. But look at everything it took to be able to do that. An enormous amount of information had to be accumulated. Information about physics, about propulsion, about the solar system and the universe and so forth, and all of that had to be combined ultimately to get somebody to do this one novel thing, which is walk on the moon. And it's going to be like that in a novelty search. You're going to have to learn something about the world in order to bootstrap from the world, to do something new in the world. So just as an example, imagine that this black dot is a robot in a maze. So this is the maze, there's a robot. If we're doing novelty search, if the robot went like that and crashed into a wall, we would be happy because we would say, well, I have never seen anyone do that before, so this is good. Well, good. But then maybe later a child will be born who does this. And I would say, oh, this is good too. I never saw someone crash into that wall, so it's a new wall to crash into. And somebody might crash into another wall and so forth. But the thing is, one day, eventually, all the crashes that you could imagine will have been exhausted. And then you're in a magic moment because there's only one thing left to do. And you have to do this at that point. You have to learn what a wall is. Because eventually, someday, you're going to have to avoid the wall to do something new. And at that moment, you have accumulated information about the world because you have learned what walls are and how to go around them. And so inevitably, in order to continually to produce novelty, sophistication will actually increase. And in some sense, intelligence has to increase because you have to learn to use the world and work within the bounds of reality the way that it's defined. So let me show you a little experiment to show you what this is like. This is a maze navigation domain, and this is chosen not because mazes are fascinating, but because it's easy for you to see what it's like to be deceived in a maze like this. You can actually see deception, because imagine this. Imagine that there's a robot that starts here, and it's going to be a robot. It looks like this. It has rangefinders, so it can see the walls, and we want to evolve a brain or a neural network that will cause the robot to travel through the maze and get to here, which is the final target position that we hope the robot will achieve. Now, I want to point out this is not pathfinding. It's not A-star search. We're talking about actually evolving the brain that would drive the robot through the maze. So it's a much more complicated problem in some sense. It's an unknown solution, like what kind of neural network would create a robot that does that. But now, traditionally, if you had a normal objective function, it would be something like the closer it gets to the goal in its trial, the better it is. Right? That's a normal thing to say. But in the maze, you can see why this is a deceptive idea, because if it got like, over here, it would get a high score. It's close. But of course, this is a cul-de-sac, so it's really in a bad place. Actually, it would be nicer if it went over here, because this is more on the way, but this is worse in terms of the objective function because it's farther away. So this is just an explicit illustration of deception. The point of this is to show you the effect of deception. Of course, there are other ways we could do things in here, but I'm doing this because I want you to see what deception is like. And so it's a good model for deception. So let's try three things. First, we'll do an objective-based need, where the fitness function is the distance to the goal at the end of a trial. There'll be a limited time for the robot in the maze. It'll try to do something. Wherever it ends up, the distance will be its fitness. Traditional kind of objective function. How close are you to your goal? Then we'll do novelty search. In this case, what we'll say is you're good if you do something new. So we'll reward the robot for ending somewhere different from where other robots have in the past ended up. So the separate novelty searches will be run, and this search doesn't even know what it's trying to do. Then we'll do also neat with random selection, just to show you what I mean when I say novelty is not random. So it's a control. So what do you think works better? Trying to solve the problem or not trying to solve the problem? And of course, you're probably anticipating it's way better to not try to solve the problem. This is, again, these are more weird results. So the objective-based need, this is what we found, only succeeded in 3 of 40 runs. We tried 40 times to get a robot, to get a brain that could actually drive a robot through this maze. 3 times out of 40. Random selection was actually a little bit better. 4 times out of 40. So once again, if that was the end of the story, and I published this result, I said, we tried need in the maze, and it's horrible, it's worse than random search. You'd say, well, need is a really bad algorithm. What are you using that for? But the thing is, that's wrong, because look at the other result. If you use novelty search, it solves 39 out of 40 times. The search that doesn't know what it's trying to do is the one that solves the problem every time, almost every time. The problem is not in NEAT. It's not in any particular algorithm. The problem is in the objective itself. And so let me show you, I'll give you an intuition about why that is. This is a visualization where I'm going to show you is points accumulating over time. Every point that you see is the last point visited by a robot in its trial. So you're actually going to see evolution progressing. This will be over the course of evolution. At the same time, in a typical run of novelty search and a typical run of fitness, and we'll see where the robots are getting in their trials. And what you're going to see is that at first they're quite similar. They're just sort of exploring this near area. But the problem is this fitness starts to commit to this area because it has such high fitness, whereas novelty search gets bored because it's not novel and it starts ejecting the search out here into the other areas of the space. Now fitness had a chance. I mean, look at these points. These are good. But the thing is, it abandons them because they have lower fitness. It just wants to invest over here. Whereas novelty search just wants to keep doing something new. Eventually it pushes the robots over here. And so eventually we get robots that have brains that will drive them all the way to the goal, even though we were not looking for them. This kind of result has been repeated in a lot of domains. So just to show you one other, think about biped walking. What do you think, if I was trying to evolve a brain to get a walker to walk as far as possible, I want a really far walker, what do you think is better to do? Reward distance traveled, which is the traditional objective, and this has been done many times in many publications, or reward ending somewhere different. That would be novelty. So in other words, if the robot falls on its face, that's good, as long as it falls on its face somewhere different. Which one do you think leads to better walkers? Once again, what we found was that the novelty search found significantly better gaits. The best ones were twice as good. In fact, I want to just show you a video because it's easier to look at that than some numbers. These are the best ones that were found from fitness and from novelty. And you can see it. So it's just really interesting that it's so much more fluid of a walker when it wasn't trying to learn to walk. And in fact, yeah, the fitness one is a little bit drunk today. Maybe he was at dinner last night. But now you do think, well, why exactly? Why? Can you help me understand? Why is such a weird result here? Well, the reason is just the same reason again. Think about the stepping stone paradox. The stepping stones to walking don't resemble walking. That's just too bad, but that's the way life is. You know, it's important, for example, to be able to walk, to be able to oscillate, you know, to do this kind of a thing. Well, you may find an oscillator, you may find one, but it may fall down right away. And you would penalize it in a normal objective-based search because it's not walking farther. But that was a mistake because that actually is a really important stepping stone. And so the stepping stones that lead to the final product do not resemble the final product, and this is why it's better not to look or to judge your progress based on how it relates to the final product. Now, there's been many outcomes like this. This is just a smattering, and there's been many this year actually, several actually from Portugal as well, from some of your colleagues. And so there's been a lot of evidence accumulating that this phenomenon is real, and I've shown you a lot of evidence for it now. And so I want to talk a little bit about what it means. I want to call search processes that don't have objectives, I want to call them treasure hunters. Because every stepping stone is a new treasure. It's something interesting in its own right. It's something we collect. And as we collect more treasures, we can get to more treasures. So there's no final objective in these kinds of treasure hunting search or stepping stone collectors. And there's several, there's not just one type of search like this. I mean, think of pick breeder as a stepping stone collector. There's no final objective. It's not like the whole world is looking for the skull. Nobody is unified in purpose at all there. Novelty search has no final objective. There's a particular thing it's looking for. It's looking for everything. I would claim natural evolution is like this too. There is no final target for natural evolution. You are not the ultimate objective, sadly enough. And neither is anything else. It wasn't designed to create birds. It wasn't designed to evolve human-level intelligence. Those are not objectives. And that, I would claim, is the only reason that such amazing things were discovered, is explicitly because they are not the objective. And so these kinds of searches, these treasure hunting searches, are extremely powerful. By collecting stepping stones, they can find amazing things. They head everywhere and nowhere. But, and it's really important to emphasize this caveat, they are not always solutions to particular problems. There is actually a trade-off here. I'm not offering you the Holy Grail here. That would be naive. Because if you think about it, you can't always get where you want to go just by searching for novelty or just by collecting interesting things. It won't necessarily give you what you want. If we reran Pick Breeder, started over again, you know, square one, 6 years ago, there would never be the skull discovered again. We would never discover that same image again. If you reran Earth, you probably won't find humans again. But you might find something interesting in both cases, something equally interesting, but not the same thing. These are searches for finding interesting things. They are not searches for finding specific things. That is the nature of creativity. They find things we could not find any other way. So great discoveries are possible, but we have to abandon the need to control what they will be. This is a tough trade-off to accept. It's not what you want to hear. In AI, we want to say, we have an objective, we set the objective, and then we make it go to the objective. That's what I want. But I'm telling you, that's not going to work. You get amazing things by not trying. You see, if you want to commit yourself to objectives with confidence and consistency, if you want to know you can get where you're trying to go, you're going to have mediocre objectives. That's how it works. Mediocre objectives are achievable. They're reliable. Search algorithms can find them. That's why a lot of the things that search algorithms do discover are not so exciting, because we are implicitly setting our goals modestly, because we know implicitly, we understand this principle. You're not going to find human level intelligence by setting the objective function as an IQ test. Who would ever do that? Because it just isn't going to work. But things like that can be found, but they can only be found by not looking for them. So now, I want to take a kind of a really strange turn. I want to apply this now much more broadly than just search algorithms in AI. As for the end of this talk, I want to ask you, why would society, why would human life be any different from in the computer? Amazing discoveries are less likely as objectives. Think about the pick breeder skull. So I want to ask you, why do we frame almost every great endeavor that society engages in terms of objectives? Why are we doing this? And what is the cost of thinking this way? Could we behave differently? I want to call this erroneous commitment to objectives, this obsession that we have with objectives, the myth of the objective. It made an abbreviation, MOTO, MOTO. So that's the myth of the objective. It's everywhere. And I want to show you a little bit. Let me show you a few examples to end this talk of where we find the myth of the objective. Think about education. Education. So it's a big topic is, at least in America, increase student test scores. We all think this is really important. Everybody should get better scores. And if they did, like if 100% of students got 100 on every test, this would be a great achievement for the country. Is this the right approach then? Reward schools, and we're actually doing this, reward schools for higher scores. Because our objective is to get the maximum score. So we have an objective, and we basically follow this objective function to the optimum. Well, no, that's the myth of the objective. Because you can't assume that higher scores are the stepping stone to higher scores. I mean, if you talk about complex search spaces, what could be more complex than educating a young person? It's extremely complex. You really believe that there's going to be this just monotonic increasing thing where just getting higher scores leads to getting higher scores, eventually everybody's perfect? It's almost certain to be deceptive. We're making a mistake by following this gradient. So you may think, oh, well, this is what we need to do. This is what other people say. We need more accurate assessment, accuracy, accountability. Let's get more accuracy. But that's the myth of the objective too. Accuracy doesn't matter if the problem is deceptive. That's what we've seen. Because if the stepping stones don't resemble the final solution, who cares how accurate you are? I mean, imagine this. Okay, Portugal creates a new department of skull breeding. It's a new branch of the Portuguese government. Because everybody wants to be able to breed this amazing skull. And so what they do then is they hire world experts in skull identification, the best in the world. These guys know what skulls look like. And because we need to have accurate assessment if we want to get skulls, right? We're going to have the best assessment in the world. But this would be pointless because the stepping stones don't look like skulls. We've seen this. This is a very bad strategy. So this is the myth of the objective. So you may say, well, so what should we do? Nothing. This is not a very constructive criticism. Well, let me suggest something. First, I want to just know that I'm no expert in education at all. But I just want to point out, just to get your thinking, that there are other ways of thinking. Imagine if we just use peer review. In other words, you're a teacher, and at the end of the year, you make a report which shows basically all the tests you've given over the year, all the assignments you've given, your teaching philosophy, the curriculum, and so forth, and then you send that to some peers, maybe blind review. So peers, other people in the country, and then they basically report back with some assessment. So you get back some assessments, so sort of like paper reviews. This would preserve oversight. So basically what we're saying is you can't just get away with being a really bad teacher because people are still watching you. But more interestingly, this collects stepping stones because ideas will spread through the network, right? There's a social network now. I have some innovative ideas. I can try something new. I could take a risk, and then someone else will see what I did. And then if that turned out to work really well, now they know about that. And ideas go in both directions. Both the people writing the reports and the people writing the assessments are sending ideas back and forth to each other. So the best ideas spread through the network over time, and this promotes diversity. And it is a stepping stone collector. It could be a stepping stone collector. It's just one alternative, and it shows that you can have stepping stone collectors. I'm not sure that this is the greatest idea. Like I said, I'm no expert. Probably people here are more. But it shows you can create, you can refashion society to be more in the shape of a stepping stone collector. What about science funding? I know I found you guys have a science funding organization. We have NSF in America. How do you encourage creative discovery? I mean, isn't that the point of science funding? How does this sound? This is the current model. Require an objective to be specified in the proposal. Now that's sounding really great after everything I said. And then have your peers assess the likelihood of achieving the objective. This is basically like how science funding works. That's the myth of the objective. I mean, setting an ambitious objective means finding it less likely. So of course no one will set any ambitious objectives because they know that implicitly. So they're going to do things that are basically modest, and because they want their peers to assess that the likelihood of succeeding is high. Now, not only that, but consensus is the enemy of discovery. I mean, this system basically supports consensus, or builds on consensus, because you need your peers to agree that you have a good idea. Well, but we saw that the whole fuel for discovery is disagreement. It's the fact that other people are doing things you wouldn't do that is important. You know, that's how we're getting all these stepping stones to be collected. So what we're doing here in science funding is the opposite of basically what leads to creative discovery. The probability of success, when it's used as a metric for progress, is a recipe for mediocrity. We should not be judging things based on, if we want creativity, based on whether they're going to succeed in an objective. So what else could we do? We should be able to consider whether things are interesting, even if they don't have a clear objective. Because that's a hard thing to swallow. But this is basically, you know, this is a principle that falls out of what we've been seeing. Disagreement should be encouraged. If you get the experts to disagree, you're at the borderland of knowledge. That's exactly where we should be looking, is when we don't understand and we don't agree, even though we're experts, on whether this will lead to something that we want or not. But this is not how science funding works right now. Let me finally talk about the field of AI. If you think about artificial intelligence, our field is a search for algorithms. You can think of it this way. The scientists are the search algorithm. We are creating new algorithms and models. And so we are collectively together searching a space, the space of algorithms. And so the same principles will apply here. In some sense, publication is like sharing a stepping stone, right? I publish my idea, then you see my idea, and you may build on my idea. And so we hope to be facilitating a creative search as well. So, given that, what should be the criteria for publication to help us discover the best algorithms? You know, we're talking about sort of meta-level search now, at the level of a field. Should it be better performance? My method performs better by 5% than your method. Great. This seems to be very important in a lot of papers. Theoretical guarantees. Should these be the criteria that would lead to innovation in the algorithms in AI? No, that is again the myth of the objective. These are objective gradients. It's not necessarily the case that higher performance leads to even higher performance. That's the myth of the objective. The stepping stone to fantastic performance may have lower performance. You know, sorry, that may not be good news, but that's true. If we always reward increasing performance, then we are sure to be deceived. This cannot possibly be a simple search space that just has a monotonically increasing function to the top of the AI hill and we get human-level intelligence. There's no way it works that way. So we should not be focused so much on higher performance. Same with guarantees. The stepping stone to the best guarantee may have no guarantee. There's no meta-guarantee that things that have guarantees lead to other guarantees. There's nothing like that. So if we always reward guarantees, we are sure to be deceived because sometimes things that don't have guarantees lead to better guarantees. We can't always follow these paths. We should be able to reward interestingness. Once again, this comes up, this idea of subjective interestingness, of the idea of what it makes a good stepping stone, something interesting, something with potential. Intrinsic potential is interestingness. And it's hard to accept, but nothing can guarantee progress at the meta level. We want guarantees. That's why we're looking for these metrics, like performance or guarantees, because we want to feel confidence. But unfortunately, nothing can guarantee progress. There's nobody that could ever know that the donut leads to the skull. Imagine if the skull is true, like human-level AI. No one can ever know this donut is leading there. All we can ever say is the donut is interesting. And it's a good thing someone did say that, because otherwise there would be no skull. Now, our minds are all we have. That's what it means. At the meta level, we can analyze individual algorithms, but at the meta level, at the level of the field, we only have our minds. We should use them to decide what we find interesting. We need to collect stepping stones as a community. Now, if you live in the myth of the objective-driven field, a field driven by objectives, this is the kind of curve that you will see over time, performance over time. It's going to go up a bit and then blah, blah, it's kind of mediocre. If you live in a non-objective field, a treasure hunting field, yeah, sometimes performance goes up. I'm not against that. But sometimes an interesting algorithm has a worse performance. It's interesting for other reasons. But that could be revolutionary. This could be the stepping stone to here. And we would never get there if we were always obsessed only with going up monotonically like that. So this problem applies also to our own community. And finally, even your life. You know, I'm sure you have some objectives: marriage, career, happiness, so forth, fame, fortune. Some of you already famous, some of you working there. Is this a good strategy? Should you make choices based on whether they seem to bring you closer? I mean, I don't even have to answer the question at this point. That's the myth of the objective. Sadly, it doesn't mean you should never do things. I mean, if your goals are mediocre, yeah, you probably will achieve it. But if you want to do like amazing discovery, something like that, become the world-famous scientist, probably not. But if that's your goal, everything you do, you measure against. So you're looking for it to make $1 million, so you don't take the summer internship because it's not paid, even though it's in the area where you have the most passion. I mean, this would be not a good idea. So this applies to just about everything. There is a non-objective alternative, which is to follow your heart. Now, I'm not claiming that this stuff works like a guarantee. It will not always work. It's very risky, but nothing will always work. That's the important thing to understand. The point is, this is the only path to greatness. Greatness, though, is undefined. That's the thing you have to accept. You don't know where you're going, but you may be able to go somewhere great. If you're afraid of that ambiguity and not knowing and the possibility of failure, of course, don't do this. It's dangerous. Follow your passion is dangerous advice. But fear of the unknown was never the companion of great discoverers. Embracing the unknown is part of being a great discoverer. So you can succeed with objectives, but your achievements will be modest. Just 2 minutes. Couple last things. Just a couple quotes I want to put. Here's Steve Jobs talking about how he got to the idea of the Macintosh. If I never dropped out, if I had never dropped in on that calligraphy class, then personal computers might not have the wonderful typography that they do. Of course, and here's the important part, this is where non-objective search comes in. It was impossible to connect the dots looking forward when I was in college, but it was very, very clear looking backwards. It's exactly the kind of thing that I'm talking about. And there's a couple other nice ones. I like to seize from every moment its unique novelty and do not prepare your joys. Or this, a good traveler has no fixed plans and is not intent on arriving. And here's this kind of slogan that we came up with for novelty search. To achieve our highest goals, we must be willing to abandon them. And all of this, interestingly, comes from designing search algorithms on computers. Thinking about artificial intelligence. Thank you.
Thank you, Ken, for this amazing talk and spreading the novel message.
I have no goal here.
You have no goal. As I said before. So it's now time for a few questions, please. Luis.
Okay. Well, it's tricky in the sense that if I consider your talk interesting, I think I was you played me into doing that because it is the good thing according to novelty, right? But right. It was a very very interesting talk and very well prepared.
Thank you.
I'm sorry to go into from such high goals or high areas where you were talking about, and ask you about the use of novelty search in plain function optimization.
Right.
For instance, those well-known deceptive functions of the CECs, etc., etc. Have you tried it on those kinds of functions, and what results have you obtained, and also compare it to these complex situations? Of course, maybe.
Yeah.
Okay.
Yeah, that's an interesting question. So, I mean, if you think about benchmark optimization problems, I mean, how would it do on those kind of problems? My group has done very little of that, but actually Trujillo, which is he's a researcher in Mexico, started doing that this year. He came out with a number of papers where he tried to use genetic programming on a whole slew of benchmark problems with novelty search versus with a regular objective optimization. And he was finding basically that for easy problems, and this is basically what you would expect, if they're easy problems, then novelty search is a bad idea. It doesn't work very well compared to the objective optimizer. But on the hard problems, it was much better. You know, that's sort of intuitive because it's a waste of effort if it's easy, because basically that means that there is a pretty clear gradient, it's not very deceptive. It's a waste of effort to be sending the search all over the search space when you could just be focusing on going up that hill. So it looks like, I mean, these preliminary results look like it may be better for some hard problems. But I would be cautious, though, about thinking about it as like, you know, a solution in general to all optimization problems. I think if it's hard enough, I would say there's no good method, probably. It's not necessarily like novelty search is the great alternative that will always work. In some sense, like something that, before I saw Trujillo's results, I thought that that it would be worse to use novelty search on things like just regular optimization problems than, say, control problems like the robot, because there's fewer constraints in the world. In some sense, like the physics of the world is a constraint on the search space. Like the fact there's walls means that like you can't go through a wall. So this creates a constraint, so we don't explore all these impossible things that are of no interest, like, you know, robots that try to go through walls. But in like an optimization problem, there's less of this kind of implicit constraint in the world, and so it's much more liable to just go off into the crazy areas and just look at all kinds of crazy things. So I wouldn't necessarily trust that it would always work really well, despite that there's some evidence, in some cases, that maybe it is actually a good alternative.
Thanks. I like your talk a lot, especially I like the attitude that you keep towards the thing, and I think it's a lot of food for thought. And I was worried while you were talking about two opposite directions, like some kind of understatement, some kind of overstatement. Mm-hmm. The understatement is, if you're not looking for something, isn't it possible that most of the times you pass through it without recognizing it? That's the understatement, okay. Because you're just not looking. And then the overstatement is that maybe you are just generalizing a bit too much on what you found with your research and try to overcome, to get the world out of it. Because the overstatement is that if your aim or you reward novelty for your own ideas, aren't you promised to fail to get novelty?
Okay, so the understatement is so this idea that actually, sorry, remind me the understatement again.
You can just not miss the thing. I mean, you're not looking for it.
Oh, if you're not looking for it, right? Yeah, yeah. So this is a common question for novelty search. Is that so we're doing this search and we're basically just collecting stuff. But how do we know when we find what we want? I mean, that's sort of what you're saying. Of course, one simple answer is it's not hard to just check, you know, externally, or to have some external check that says, well, no, I don't think it's cheating, because what's important about the algorithm is that the algorithm itself is not driven by the check. There's nothing harmful about having an external, check or a binary question of, you know, has this solved or not. We can just stop it when it's solved. I mean, it's just a stopping criterion. But that doesn't affect the search, though. It's not actually the search criteria that drives the search. But I think there's a deeper answer to this than just that. Because in a large part, I think that these kind of searches, these treasure hunting searches that I'm calling them, are not about finding something in particular. At first, people will use them for that, and that's what people have been doing, is trying to just say, well, this is an alternative to optimization. But I think in the bigger picture, they're more interesting as just creative searches that find interesting things in general. I mean, you can have a space, and you can ask, what's interesting out there in this space? And this algorithm can collect everything. And if you're doing something like that, which I think is really an interesting possibility, people have started to do some things like that, then it is harder to say, well, what should we then collect? What should we look at out of that archive that's collected? Which are the right things? Which are the good things? That's a tricky question. I think, you know, what we've been doing is things like we've been putting up visualizations on the screen, like we do a PCA on the behaviors of the robots, and then actually look at all these dots on the screen and start to understand where the interesting stuff is. We have to do it by hand. You know, we could say in this corner, you've got like guys that like jumping, and here's the hoppers over there, and there's the runners over there, and we sort of understanding the layout through this kind of analysis of the archive. So yeah, it can be tricky if you don't have a very specific stopping criterion. Okay, but the overstatement in terms of am I overstating this principle based on the research? I mean that's a clear concern. I bet a lot of people agree with you that that's something we should be worried about. You know, should we all drop objectives and stop trying to do what we're trying to do? But I guess I'll stick to my guns here. I mean, just if you don't believe me, think about what I've shown you and what I've said, and just try to convince yourself that you know what the stepping stones are to doing something amazing. I'm not talking about stuff like making lunch. You know, obviously you want to make lunch. Going to the refrigerator is a good idea. It's probably where the bread, you know. So you know, there's lots of modest things in life, and including like you want to become an accountant. I mean, go to accounting school. Like I mean, that's a pretty clear stepping stone. These are not ambitious. That's not what I mean by ambitious objectives. But if you want to do something amazing, I think you could agree with me. There is no formula for that. If there was, we'd all just do it, right? I mean, if there's no formula for being amazing. The way to be amazing is indeed to follow your passion, to identify interestingness when you see it, and it just happens some of us are better than others at doing that. Some of us have a nose for the interesting, and some of us don't, and I think a lot of people have a sense for their own self, whether they're good at that or not. And if you happen to have that talent, you know, that's basically a talent for serendipity, well, you probably, it's a good idea to follow that.
Is that the interesting is the new objective. And people might call interesting different things.
Yeah.
The only thing is that it's not specified. It's just
right.
interesting.
Right. Yeah, so I mean, that's...
So in your own terms, it's a promise to fail to be interesting.
Yeah, so I mean, we should disagree. I mean, you may think something's interesting, I don't think so.
Let's go to the next question.
Okay, we'll debate later.
Hello. Thank
Hello.
you for your very nice talk. I find it quite, let's say, zen. I was wondering just one, just one thing. Have you looked at the structure of the evolved neural networks? Did you find some interesting structure there?
Yeah, that's a good question. So the structure of the neural networks that come from this algorithm, we notice a difference between even if the problem is solved. So we can sometimes solve the problem with the objective-based search, not as often in some cases, and sometimes with the novelty search. And even if it's solved, we find that in the novelty searches, the networks are significantly smaller. Always. It's very consistent. There's different reasons for this, but one of the reasons is, if you think about this is also interesting, is that there's such a thing as a bad kind of a success. And because if you're in a search process where complexity can increase, and if you're looking for an objective, even if you succeed, it tends to be that the way that you succeed is by making little minute changes, little by little, basically patchwork or piecewise solution, because any little thing that you do that increases fitness by a trivial margin ends up getting incorporated into that final solution, and it starts bloating. Whereas a novelty search is about fundamental changes. So, you know, it's saying if things totally change, then this is something we're going to follow. So it tends to end up with a much more compact, less piecewise, because novelty search is not interested in small incremental changes. They're not novel. So it ends up with much more compact solutions in the end, which is an interesting side effect.
Okay, it is a question related to the first one. I have the feeling that all the problems that you have shown have two precise characteristics.
Yeah.
The first one is that they actually are deceptive. Think about the maze problem. In order to get closer, the only way is to get farther away to the goal, okay? Mm-hmm. So this is a classical trap function, okay? Yeah. Presented in a different way, but this is a trap function. Mm-hmm. And the second characteristic is that the number of bad behaviors that you have to learn is limited in number. In the maze problem, you have 4, 5, 10 walls, okay? Yeah. So I would like to see novelty search applied to the other way around, to problems in which fitness has a clear gradient towards the global optimum, and problems in which you have, say, 10 raised to the power of 20 local optima that you have no way to store and to learn.
Yeah, yeah.
What do you think would happen in those cases?
So good questions. So the first one is basically the case where you are able to just follow a very straight shot to the objective. And like I said, novelty search is not a good idea if that's the situation. I don't think it's going to do well. It will probably solve the problem because it's an easy problem. I mean, by definition, if there's no deception. But yeah, if there's no deception, you don't need it. So, you know, I would say use a regular objective optimization in that case. But you know, I think just about every interesting problem in life is deceptive. It's sort of by definition, at least for me, if it's not deceptive, it's not interesting because it's easy to solve and it basically don't need a search algorithm. I could do almost anything and it would be solved. So I don't think that's really the interesting case. Now this other case is much more deep and interesting. If there's like too many behaviors, and there's many ways of thinking about what that means exactly. But it's like there's an overwhelming, like you said, 10 to the 20th or something, number of, maybe I'd call them stepping stones or something, and you need to traverse all of them to get to this thing that you're hoping to get. Yeah, the message is that it won't probably get it. You probably won't find it. The space of behaviors is too big. It's just overwhelming. But I think it's important to emphasize that's not what I think this search is for. This search is for finding something interesting. It's not for finding a particular interesting thing. I mean, you're talking about a case where there's a particular thing we wish we could find, and there's so many stepping stones to it that it's just basically astronomical. So yeah, I don't think we'll find it. But if we're willing to give up the idea that we have to find one particular thing and this is the only thing of interest, we may find things that actually are that far out. It's just we won't find that thing. We can go really deep into the search space with this kind of method. It's just not to get to a particular point. And if you look at these kind of searches, like these stepping stone collector searches, like nature, they do go really deep. I mean, humans, for example, human intelligence was evolved. It was discovered by a search algorithm, in effect, but not because it was the target. And I don't think if you reran Earth, you'd find humans again. So, so I think it's better to think of it that way. Think of it as just an interestingness search, but not a search for a particular thing.
Two final questions.
Oh, thank you very much for a very inspiring talk. I have always been a critic of people wasting time in Facebook, so I'd like to see your opinion about, are we going to something interesting, to some novel? Find something new by wasting time using Facebook and other social networks.
Okay, I've never thought about that in reference to this idea. So I see what you're saying. Like, it could be that, yeah, this is actually a stepping stone collector because it's a network. I think if we wanted a social network to facilitate this kind of discovery, I wouldn't necessarily design it like Facebook. But maybe Facebook has a little bit of this effect just because it is a network. But I mean, one of the problems with Facebook is the tendency to close you off or wall you off with just your friends and acquaintances. I mean, I think you want to be exposed to people who are very foreign to you if you want to have ideas percolating through the system in the kind of pick breeder way. So yeah, I would change some things about how it's really set up. But I do think you're onto something there. Maybe there's something about social networking in general that is compatible with this idea. That's true.
My own question and comment. So, on one hand, I tend to agree with you because you, as a good American, you are under Christopher Columbus syndrome. I mean, who discovered America, but intended to discover something else.
Good example.
India,
yeah,
in
yeah.
fact. So these things happen in real life.
Yeah, yeah. Right.
On the other hand, if you are guiding search by novelty, why, in that example, how can you measure the success that you get to a target? Why did you stop searching when you found out a car, which is a very traditional picture?
Yeah, there's a lot of parts to that question. That's an interesting question. I mean, it goes back to similar to the question that was asked earlier about how do you identify when you've arrived somewhere. I don't think actually it's that hard of a problem. If it's just that question of, you know, how do you know when to stop? And I stopped at the car was because I recognize it looks like a car and I like cars. But I wasn't searching for a car. It's important, I think, to separate the stopping criterion from the incentive or constraint in the search. Like, those are two separate things. So I can drive my search by different criteria than I stop my search. But yeah, in a larger sense, I mean, you know, you may feel some skepticism about, like, is this really always how things work? Because it is so kind of ambiguous what exactly anyone's trying to do. Like, do scientists really not know what they're trying to do most of the time or something? But what you have to remember, though, is that what we do and what we accomplish is built on the shoulders of our predecessors. I mean, they have laid stepping stones for us. So sometimes it becomes realistic to have an objective because somebody has created a stepping stone that's close already. You know, if there's already a face on PicBreeder and I want to get a sad face, that could be a good place to start. And maybe it's realistic now at this point because I'm starting from somewhere that's in the valence of that attractor in the search space. So I have a chance to get kind of where I want to go. But in general, yeah, I don't think that there's a real problem with that ambiguity, or maybe it's that people who are good at this deal well with ambiguity. Like they have a nose for ambiguity and interestingness and serendipity. And in fact, if you go to Wikipedia, there's a page on serendipity. It's real interesting. It has like dozens of serendipitous discoveries listed. It's just interesting to see like how common this phenomenon is, that people find things they weren't looking for.
The case that you are looking for a more abstract objective, like without a recognizable image, but it's an objective.
No, I think that's another good question. I think that's not the best way to look at it. You could think of it that way, but I think what's important is to look at the search globally. Like PicBreeder is a global system. It's true that an individual player in the system may sort of like cars or something, or maybe they have like a set of thousands of things they like. You could say they have thousands of objectives. But the system as a whole, as a unified system in aggregate, there's no unified objective in the system. That's why the system is working. What you like and what I like, they may be disjoint sets. That's necessary. So what's important is that the system together has no unified objective.
Thank you. Thank you so much.
Thank you. Thank you.
Very good, very inspiring.
Thank
I still
you.
have another objection, though.
Okay.
It's not really an objection. I liked it a lot.
No, I understand.
Let me congratulate you.
Sorry.
Thank you.
Congratulations.
Thanks.
Fantastic.
I appreciate it. I leave Saturday, actually.
Do you want to take that one?
Oh, yeah. Sure.
About this thing.